Well, thank you very much, Pat. So now we open it up to the audience for questions. We have the panelists and Claire, and we also have a few that have come in via email, so we may take turns with those. And again, if you step up to the microphone, speak into the microphone, and introduce yourself and who you're affiliated with, if you're affiliated with someone.
Yes, my name's Steve Burrell. I'm an independent consultant. Is it possible to bring Tom's slide up there that showed the particular line where he'd added the colorations on it?
Can you turn that? Is this the one you're interested in?
Let's see. There was another one, wasn't there? That one right there. What the PAG material, given well, just my rough estimate is that we're talking a sulfide content of definitely less than 20%, maybe even in the 5% range total sulfides. And so, am I correct in saying that 5% of the mass of the rock would fit into the PAG category and 95% into the non-PAG?
I don't think you can interpret it. Yeah. I mean, this is, well, maybe I should let you answer,
no,
but you're basing
the microphone.
Sorry, you're basing that on, I guess, the sampling density and the number of sampling points that fall into the different categories on that diagram?
No, I'm just basing it on the amount of sulfur that we saw yesterday in samples. Do we know what the percent of sulfur in the entire deposit is?
I showed some frequency plots. I don't know if you remember that showed the distribution of sulfur according to the exploration drill hole database, and that showed that there was quite a variable distribution of sulfur, and the range of sulfur contents was influenced by the rock type, whether it was the tertiary or the pre-tertiary. So I guess the density of sulfur varies through the deposit.
I understand, but if you looked at the entire deposit in aggregate, what's your best estimate of the amount of sulfur material there, the amount of sulfides that are within the deposit?
Gosh, well, maybe I could throw that over to one of the pebble geologists, actually, because that's partly a question of resource size.
Well, and the point being on Tom's graph, my estimate from looking at it is it's definitely somewhere less than 20% would be on the right-hand side of that graph, and so I'm just saying a large portion of that material is going to be non-acid generating material, it would appear, right there off that. And not based on those samples at all, but based on the overall deposit. Is that
The problem in thinking about that is you can't just look at a sulfur content analysis for the whole deposit and then decide how much of the material will be acid generated and how much won't. It really depends on individual, discrete samples throughout the pit volume.
I agree, but there is going to be an average.
There is.
Once you've discreted all the samples, there is going to be an average, and that's my basic question.
That's true, but that gets to my point about heterogeneity in these piles. So we can't really treat these things using the average numbers because they're not homogeneous.
No, but for the general public to be able to put it in some kind of perspective, let's say they're moving 1 million tons of rock. Out of that 1 million tons of rock, there's a small portion that is potentially acid generating.
Right. Well, let's go to the previous slide if we could, just for a minute. So these are for the rock.
Okay.
Right? The one that we looked at previously was for tailings. So this is all the pre-tertiary rock from the east zone on the right and the west zone on the left. And I don't know how many samples are represented here, but if we look at them, the ones in the red zone are the samples from each of the zones that suggest that they should be
Right.
acid generating.
Yeah.
So you can maybe look at the distribution of points above and below the blue and say maybe 10% not, maybe 80% yes, and 10% in the undecided zone. But that's perhaps a better way to look at this,
Okay.
based on the distributions here.
Let me ask another question regarding the static test versus the kinetic. Is not the static test where you're flushing that thing continuously? Is that not going to give the worst case scenario that you'd ever expect to see? If you have a finely ground material.
I think
well
you're talking
exposed.
about the kinetic test, are you, where you're flushing it progressively? That would be, well, the humidity cell test that I
Yes.
showed.
Yes.
Yeah, I mean, yeah, I agree. I mean,
Okay.
it's also known as an accelerated weathering test because it's deliberately designed to accelerate the rates of reaction so that they're readily measured, in a
Right.
laboratory timescale.
And so I guess what I'm saying is, can you then say that is likely the very worst situation that could ever exist?
Well, I would like to be able to say that, but I prefer not to be so definitive about it because
Understand.
as I mentioned, there are other variables like temperature and reaction rates would increase at elevated temperatures, and if a waste rock heap were to heat up, for instance, there is the potential that even in a waste rock environment, the rates could be accelerated. Whether as much as you would see in the humidity cell test, that's another question.
Thank you.
I'd just make a comment on that. I think Claire's caution is well warranted. There are deposits around the world that are in skarn settings, for example, where, if you take discrete samples and you put them in these accelerated weathering tests, you may never see, because there's a large excess of neutralization potential. In these tests, you may never see acidification. But then you go in the field after the deposits are developed and you find seeps that are pH 3. So
Correct. Yeah, I understand that.
it definitely occurs. Yeah.
Good, thanks.
Thank you. I think we'll have a question from the email here.
Yeah, this email that came in from Ann Mace with Stratus Consulting, and she has 3 questions for Claire. And I'll just state them one at a time so you can address them one at a time.
Okay.
The first one is, how will the information on time to onset potentially be used in management of mined materials based on your experience from other sites?
I guess one of the ways in which it might be used is in the context of ore stockpiles. If an ore stockpile, if there's a plan for that stockpile to be hanging around for a few years before processing, there needs to be some understanding of whether that stockpile would go acid during that period of time, and therefore whether stockpile management strategies need to be put into place to mitigate against impacts due to those kinds of questions. So that's one way in which that information can be useful. Also, there are instances where you could envisage that waste rock needed to be stored in one location before it reached its final engineered closure location, and again there needs to be some understanding of its behaviour during that time period before final engineered management strategies are completed.
Okay. The next question is, why do you think there is not a good relationship between NPAP ratio and final pH in the humidity cell tests? What are the implications for techniques that might be used in the field for estimating whether material is PAG or non-PAG? The final pH in the humidity cell test is basically a function of whether or not that's, in the case of a PAG-classed material that's in that test, it's really a function of whether the neutralizing potential in that test has been consumed or not. It's perfectly possible that a test might run for many, many decades before the neutralizing potential is consumed. So clearly the pH would remain neutral for decades until acid onset. And certainly in our test program,
There are several PAG class samples that have yet or did not go acid during the time period that the test was run, and based on our calculations, we basically estimated that it could be decades before the test would be expected to go acid, and at some points you need to decide whether or not there's value in continuing that test or not. There are some tests in the program that are continuing, that are in that kind of period of lag time before acid conditions develop.
And the last question, which is kind of a follow-up to some of the previous discussion, you use calcium and magnesium concentrations to estimate the site-specific criterion for identifying PAG rocks and come up with a value of 1.6 for both pre-tertiary and tertiary rocks. Do you know what minerals the calcium and magnesium are contained in? Do you have enough pre-tertiary humidity cell samples with NPAP ratios greater than 1.6 to evaluate the usefulness of the site-specific criterion?
I believe that the calcium and magnesium are coming from calcium and magnesium carbonates, so calcite and dolomite. So that answers the first part.
So hydrothermal dolomite has been identified.
There is dolomite. It's not as widespread as calcite. So calcite's present. Well, I say widespread. It's present in some of the alteration cements. The NPAP critical ratio is not actually a function of the overall NPAP ratio of the sample. It's actually a function of the relative rates at which the NP and the AP are being consumed. So I don't think it matters that the pre-tertiary dataset didn't include samples with a high NPAP ratio. In fact, there are very few pre-tertiary samples that have a high NPAP ratio. Most of those material types are PAG, so it's more a question of the relative rates at which the different reactive components of the samples are consumed.
Thank you. Are there any panel members who'd like to add any comments to that discussion?
Well, I just re-emphasize that this value of 1.6, I think, requires some additional thought and consideration of error bounds. This definition of a critical NPAP ratio and relating to the last question could also be affected by the time scale of the humidity tests. So that's also something that could be important to consider in using that method to define that critical ratio.
By that, do you mean you expect that ratio to change as the test progresses?
Well, in this case, if the pre-tertiary rocks all have NPRs less than 1 for the most part,
Mm-hmm.
and then you do the humidity cell tests and you reach a steady state, and that tells you that you have a critical ratio of 1.6, and it seems that you haven't conducted the tests to the point where all the NP's exhausted and you still have some AP. So,
as soon as the NP is exhausted, the test goes acid, and that critical ratio no longer applies. I mean, you've gone beyond the point at which it applies.
okay.
All the data that I showed on that diagram was from tests that were still running at neutral pH. So therefore, the neutralization mechanism was still taking place.
But it will become acidic at some point, likely.
Some of those samples, yes,
Yeah.
will
Yeah.
definitely become acidic.
That's right. Yeah.
Go ahead, Jeremy.
Yeah, I guess sort of continuing with this trend of time, and I don't want to sort of feed you your lines, but I mean there are engineering solutions to dealing with acid-generating materials. Perhaps it would be worthwhile to actually describe one or two of the options that are available, that are out there for actually dealing with this stuff, because it does seem as though at some point in time we're going to be dealing with some acid mine drainage from either the tailings or the waste piles. So what strategies are there for actually dealing with that? Because as I understand it, there are quite standard mechanisms either for capturing that type of material. Some cases you can actually use it as kind of a leach process and actually recover metals. Or the other mechanism might be to import carbonate rocks to act as a long-term buffer for that acidity. So it might be interesting for people to hear what are some of the known options for actually dealing with acid-generating materials.
Okay. Well, I mean, you mentioned some of them. You know, one method is incorporating some sort of containment, engineered containment to the waste material, and that's the kind of solution that's generally adopted for tailings. Tailings are placed in an engineered facility. Seepage from, any seepage derived from the tailings is collected. Either never leaves the facility or it's collected and treated. So basically those materials are isolated from the general environment, and that's a solution that I guess prevents that particular material having long-term impacts on the wider environment. Waste rock's a little bit more variable in terms of the options that are looked at. I mean, containment is an option in the same way that it's an option for tailings, theoretically. But in practice, generally, waste rock dumps are managed in such a way that the reaction rates are minimised where as much as is practicable, thereby minimising the rate at which potential contaminants might leave or seep from that waste rock dump. And I guess the focus can often be on treatment technologies, collection and treatment of any seepage that might come from those materials. Another possible option that you alluded to there was blending or incorporation of limestone in the design of the waste rock dump, so that basically what you do is you introduce additional neutralising potential to the waste rock dump to try and influence the composition such that acid conditions do not develop in that waste rock dump. So there's a range of different options, and I don't know which are going to be explored in the context of this project.
I have a question which you may have answered, I may have missed, but I don't recall it. You've done these humidity cell tests longer than normally required. And I'm curious to know if they're still ongoing. Do you have tests ongoing, and how do you are you going to keep them going for quite a while?
We do. At this point in time, there are still some 30 tests ongoing. The longest running test is probably up to about 7 years now. So we have a 7-year-long data set for some of the samples.
Very good. Are there any more questions from the audience? Please step up. Yeah.
My name is Paul Frost, and I'm from Togiak, and started commercial fishing in 1969, and I'm still commercial fishing. I guess the picture I'm trying to get is how is this mine? Okay, you're doing all these studies, and are they going to just like dig a big hole in the ground? Is that what they're going to do? And then they're going to put, they're going to pile all this stuff up and then wash it with some kind of chemicals to separate the ore. I mean, how are they going to get the gold and the minerals, the money that they want to make, separated from all of the dirt? And how is making a big hole there, taking off the moss and all of the grass, and exposing that area? How is the sun, the weather, the sun, and the rain that we have, the tremendous amount of rain out there, how is that going to, how are they going to mitigate the poison from going into, we have river systems on top of the land, but we also have river systems under the water. I mean, there's water. It's all connected. It's like the cap. It's like in your body, all your veins. I mean, it's all connected, and it goes a long ways. So once if by chance, poison or this chemicals get introduced into this fragile ecosystem that we live on over there, how, I just can't, I'm having a hard time envisioning how, I hear you talking about, these PAGs and NAGs and you're gonna, but, I really am thankful for the studies. It's just, at some point, you're not going to be out there watching over and making sure that this is done. It's going to be some construction guy like me that's going to be running that 966 that's going to say, should I put this pile here or over here? And the boss is having coffee. And, you get the picture. And in the end, they start out doing the right things because I've been in dirt work my whole life as well as fishing. And and it starts out fine, but boy, when your timeline's running out and you need to make money, you're going to just move on. So how are we going to contain all this? Are they going to put a big piece of 6 mil visqueen? Are they going to cover? Are they going to dig a big hole and then put this plastic underneath there, and then they're going to carefully put the first layer in so it doesn't puncture the visqueen, and then once you have that layer on, then we're going to dump the poisonous stuff in there and then sprinkle lime over it and then sort of mitigate. Is that what we're talking about here? How are we going to? That's what I'm trying to. I'm hearing what you're saying, and I understand most of it. I'm just trying to figure out how this is all. What kind of so I can tell people when I go back that, oh, this is what they said, and this is how it's going to work, and these are the studies. I just don't have this picture. I have to see a picture.
I sympathise completely. It's a difficult picture to get, and I guess I should make the point that the studies that we've been presenting here are baseline studies to try and get an understanding of how the materials behave, and basically the understanding that we get will go into selecting management strategies or engineering strategies. Now, to get to your question was when you come to implement those strategies, how are you going to know that they're implemented properly, efficiently? How confident can you be that they're going to work? Those are really difficult questions to answer, and I guess as the project designs evolve, the onus would be on Pebble to put into place management strategies to try and ensure that whatever management strategies they decide upon are implemented effectively. So I don't know if that helps or not.
Jeremy, do you have something to add?
Well, I thought, if I may, perhaps I could give a kind of a very brief description of the mining process. To answer your very first question, because we talk about tailings and waste rock and so forth, but it's not immediately obvious what it is exactly we're talking about. Fundamentally, the deposit is a volume of rock which contains metals of economic value, but that volume of rock is somewhere below the surface, and to get at it, you have to move a lot of other stuff. A lot of that will be waste rock. It contains uneconomic values of material. So if you take the mine as ultimately being some sort of big conical pit, a significant percentage of the actual rock that you moved out of that pit is of non-economic value. It's what we call waste rock, and that's the stuff which goes out on the waste piles. Now, the problem with that rock is that although it might not be economic, it might not have economic values of copper and gold, it almost certainly has, or some of it, certainly the pre-tertiary stuff, has quite a bit of pyrite in it. And that's the worrying component that we've been talking about here, because it's the pyrite that can generate acid. So it might be waste rock, but it's still carrying some pyrite and can potentially generate acid. So the waste piles that we were talking about, the reason that they're a problem is because of some of the pyrite in that material, and that needs to be managed. The ore, the mineralized stuff, which is what the company wants, that's processed very differently. That's typically, and again, it depends on the mine design, but from what I'm hearing here, it's going to be pretty standard, that you take that rock and you crush it to a very fine grain size, sand or even finer, to the point that you can separate the economically valuable sulfide minerals like chalcopyrite, the main copper mineral. You can separate that stuff from the rest of the rock, which is usually minerals like quartz, feldspars of no economic value. So what you end up with is a crushed material, finely crushed material. You can separate the valuable sulfides from that, usually by a method they call flotation, which separates the sulfides as a froth and you skim it off. And the rest of the waste material, which is now very fine grained, goes out into the tailings facility. So that's called tailings. Now, in a typical ore, porphyry type ore, you extract most of the sulfide because that's where your metal value is. So the tailings will probably be fairly low sulfide. And that was what was illustrated on the diagram that we saw, that much of the tailings are actually non-acid generating because you've actually taken the sulfides out because that's where the money is. The concern, though, is that the pyrite is still in that system and is still considered a waste. So you try and extract the chalcopyrite with the copper, the molybdenite with the molybdenum. Now, some of the pyrite has gold, and as I understand it, they will be trying to extract that gold from the pyrite, but ultimately the pyrite is going to go into the waste stream in some place, and that's what we were talking about this morning, how much of that tailings material will be pyrite rich. And there is certainly a chance that a significant stream will be high pyrite. That'll be the stuff that they extracted the gold from. And so far, we haven't seen tests done on that potentially high pyrite material. So that's what we call tailings. Some of it may be low sulfide, but some of it may actually have significant sulfide concentrations. Now that stuff is traditionally put into a kind of like a pond-like facility, which may have a plastic lining, as you described. More commonly, it will have some kind of impermeable lining, such as a clay, some kind of material which reduces seepage. So depending on the design, you certainly design it so that you don't have leakage out of the bottom of this thing. And if you're going to design it, as we heard earlier, you can design tailings dams so they're permanently covered with water. They're called tailings ponds. And the idea there is that the water prevents oxygen from the atmosphere getting into that stuff and oxidizing it. The problem you have there is you have to make sure that that thing remains covered with water in perpetuity. And some of the, as I mentioned earlier, some of the tailings dams failures that we've seen around the world, and Canada has a whole bunch of them up north, tailings facilities that were built years ago with no real controls. It's fine when the water's there, but you get a beaver in there which sort of undermines the front of the dam, and that happens. And the water escapes from the top of the dam, then you have a very serious problem, because then that thing goes into kind of a runaway oxidation process, and you get very extreme acid generation. So what I think we're hearing is that today you would not build a tailings dam in that way. You would build a tailings dam so that you were sure that it was going to maintain its integrity for effectively in perpetuity. That would be the design objective, and that's certainly the standards that the most engineering firms would use when they're designing a tailings facility. So yes, you're going to end up with a great big hole in the ground. You're going to end up with piles of low-grade rock, which, as we've heard, have the potential to generate some acid at some point. There are ways of managing that. And then you're also going to have these tailings impoundments, which I think probably are the ones that need to be watched most clearly, because they do have the potential for major problems.
I'd like to thank the last person who came up and asked that question. This is the kind of question that can help all of you who don't have the technical background to understand more about what's going on. And that's what we're here for, to try and help you understand not only all the studies, but sort of what might go on at this proposed mine site, and how it would work. And have they done all the kind of tests and studies that are needed in the baseline report. So I encourage any of you who are still struggling. There's a lot of technical stuff here, and anybody who's struggling with that now, it's a good time to ask a question. Please, go ahead.
So, this is Milo Atkinson with the University of Alaska. You gave a good context to my question, because I understood the solution to a lot of these potential problems was submerging stuff underwater in perpetuity. And what I didn't understand is I thought that you showed that some of these subaqueous tests, you had some samples that generated acid and liberated minerals. And I guess I'm wondering about the mechanisms by which that happens, and then what that means for what might happen in tailings piles or in submerged rock in a pit, for example.
Yeah, I did show data that from a subaqueous column that was generating acidic leachate. Now, that particular sample that was in that column had already gone acid before it went into the column, and basically what the data were showing was that it continued to release acidic leachate even under the subaqueous conditions. So if the material has already consumed any neutralizing capacity while it was exposed and has accumulated acidic reaction products, then it'll take some time after submergence before those acidic products would be washed out of the sample. And it's important, I guess, to differentiate between material that has not yet gone acid. If you manage to submerge that quickly before it's accumulated any acidic products, then you've prevented the further oxidation of the material and prevented the likelihood of acid onset. But if the material has already accumulated acidic products, there will be some period of time, even under subaqueous conditions, where acid conditions are possible.
But eventually, if you had that sort of phenomenon happening and it was submerged, eventually it would stop releasing?
That would be the hypothesis, but clearly those two tests that I showed have been going on for some period of time and are still giving acid leachate. So we're going to have to spend some time looking at that data and interpreting what exactly is the source of the acidity and verifying that acidity formed prior to the subaqueous test.
Thanks.
Okay.
If I can just add to that, I don't know if that's working. I was curious about those data as well, and oxygen has a finite solubility in water. I was wondering if you looked at whether or not just diffusive replenishment of oxygen could account for the acidification that you were noting?
Well, certainly those columns, if you remember, there was a column of water that was sitting above the actual sample. That water is oxygenated water. There's no attempt on our part to exclude oxygen from that water. So there is some finite amount of oxygen supplied to the sample. But I guess my perception was that the rate of supply would be so slow that further, new oxidation, for want of a better expression, would not be taking place, and that the acid products would have leached out. So, that's something I need to revisit and examine more closely.
We have another question from the audience, please.
Thank you. My name is Donnie Flegel, and I work for Weetabix Limited. It represents 5 villages in the Bristol Bay area. And I don't know if this is a real question, but something that I was thinking of, because we take a look at these plans and we take a look at, the worst case scenarios based on our own imaginations. And if we're going to do that, is there any way that some of this waste stream can be reused for some type of economic opportunity? That's a question I have. And just a comment, I'd like to thank the scientists that have come and recognize Rick Parkin here. I enjoyed the peer review panel that came up earlier in August, and I personally learned a lot. I know it's very hard to separate all of you and your peer review panel from folks that have hired you or commissioned you to do the work, but I do want to thank you.
Go ahead, Claire.
Okay. Well, I don't really know that I can answer your question very satisfactorily. I mean, I guess really where you're coming from is, is it possible to simply remove all those sulfide-bearing waste forms from the site, full stop, by in some way processing them to remove the sulfur, perhaps sell it on, I don't know. I think it'll all come back to whether or not it's economically feasible to try and go down that road. There's certainly options on the table about what their economic cut-off grade might be. If they were only looking at economic benefit, they might set that cut-off grade at a particular value. But if they were also looking at environmental benefit, they might deliberately make the cut-off grade lower so that they actually process a greater volume of the sulfide-bearing material than would otherwise be the case. So, there are those kinds of questions are being asked, but within certain constraints. And I probably can't say anything more on that. I don't know if any of the Pebble people here might want to comment.
Anybody from Pebble want to say anything?
I'm John Shively with Pebble. I mean, I think in general you're right. I mean, the volume is too great. And the example you gave of cutoff grade is something we're discussing. The whole issue with pyrite, there are options that's come up. I mean, part is you don't do anything with pyrite and you separate it out in the tailings in an area. You could process the pyrite there, as you indicated, or there's also a possibility that we might be able to take all the pyrite and have it processed someplace else. So all of those things are things that are under consideration. But for the large volume of tailings and waste rock, for the most part, there probably is not a viable economic market for those things.
Yeah, I might just add to that's the problem. I personally believe that every bit of, quote, waste material from a large mining operation could be used for something, and the reason it's not used is not economic. Just lose money on it. But this is an area where there needs to be more thought, more innovation, and I see that happening in some places. So we are moving in that direction, and hopefully more of it will be seen in the future. Next.
My name is Sam Snyder. I work for the Alaska Conservation Foundation. Twofold question. And the first gets to actually two now comments about worst case scenarios, whether it's in the humidity cell tests, if that's giving the worst case scenario. Given Tom's point on the precautionary principle, just simply isn't that what we should be designing for as worst case scenario, particularly in a place this wet, this windy, and where the conditions are still so unknown. And I think Tom pointed out a lot of those the uncertainties with these tests in the lab as opposed to the field. And then a second follow-up to that, if copper leaches underwater and it creates under acidic conditions, it leaches, and it also leaches underwater, and selenium and so forth leach under a variety of conditions. Doesn't this mean that really success in containing potential acid mine drainage, tailings facilities management depends upon water management working perfectly? And so this goes to the mitigation technology question. Again, are there examples of other large mines of this size, of this type, in this type of place, where we have examples of that working on a long time frame that can provide that sort of confidence in the historical record of the mining community? And I'm just going to sort of book into with that and say, don't give me the Fraser River as the example, because we know that fishery's a mess. Thanks.
I don't really know how to answer that. There are, as I mentioned, there are analogous mine sites in operation, and my colleague has actually done a review of experiences at those mine sites, both positive and negative. I think in terms of positive experiences, they do tend to be more associated with recent mines. In other words, mines that have been operated on the basis of current best practice as opposed to what was best practice many, many decades ago. And almost by definition, because those are recent mines, the data that's been generated that could be used to measure the success is relatively recent data, and so therefore we haven't got a data set at the moment where we can test the long-term performance of those kinds of criteria, simply because that data hasn't yet been collected. So it's a question that's impossible to answer, really, but you know, the intent is there.
I would ask Jeremy or Tom if they might have something to add to that, because even though the mine may not be the same, well, the mineral deposit may not be quite the same, there are places in Canada with very large, extensive tailings that have been held subaqueous as a technique of preventing acid drainage. And I haven't kept up on how well that's working, but some of those have been around for, I don't know, a couple decades at least. Isn't that right?
Yeah, I think mines that were built in over the last 20 or perhaps 30 years have been built with tailings dam construction techniques that are designed to last, if not in perpetuity, but you know, to withstand the decadal storm or the 100-year storm. Whereas dams that were built, you know, 40 or 50 years ago, they were just built long enough for the owners to get out of town when they were finished, and that is a huge problem in northern Canada. There's thousands of abandoned mine sites in northern Canada that were built, you know, in the mid 1900s, where these sorts of controls on long-term storage just weren't a consideration. You know, people built them long enough, as I say, for the mine to last, and then, you know, they walked away and threw away the key. And now the taxpayer, of course, is picking up the bill for remediating those sites. And that's a major issue, but it is a historical one, and it's one that certainly the modern mining industry is taking very seriously. And literally, you know, you talk to tailings dams designers, they talk about designing their dams to last in perpetuity. Whether they actually do, we don't know, because we haven't had perpetuity to watch. But certainly there's very few cases of relatively recent tailings dams which were constructed to high specs. There are very few instances where there have been any problems. I'm not going to say never, I never say never, but I'm not aware of any recent tailings dams that have been built to high spec that are showing any signs of problems. Well, the water. Yes, exactly. I mean, the question was, what about water management? And I mean, I think that is the big question. If you are maintaining, for example, a tailings facility which is required to be covered with water to stop it going acidic, then you're saying that you have to keep it covered with water in perpetuity. So, you know, the mine is going to have a finite lifetime. What happens when the mine locks up and walks away? There are examples where there's ongoing remediation being paid for by companies long after they've closed the mine. Many mine plans require that. But, you know, again, you can project that out a few decades, but it's very difficult for us to predict whether that company is going to be around in 50 years' time, 100 years' time. Are people still going to be managing the water situation there? So, you know, I prefer to see facilities like this, which are engineered as standalone things, which don't need maintenance. They're designed so they don't need to be maintained, and that's, you know, one of the reasons for using things like carbonates as a natural buffer for pH. You build your containment facility out of that stuff so that it actually contains acid that might be generated in perpetuity. If you're going to rely on sort of maintaining a water level and so forth, I think there's a much greater risk of at some point something going wrong. And you're going to lose that water or something like that.
Yeah, I might just mention that probably the most common water management technique that's used these days for these acid drainage situations is to treat it with an acid neutralization plant. That is, you set up a chemical plant that adds lime and neutralizes the water, and then you have sludge disposal, and hopefully in a safe place. And the problem with that is that the seepage or the discharge of bad quality water from mines can go for a very long time, hundreds to thousands of years. And so those chemical plants aren't going to be there that long. And we're still, and for many of those sites, usually abandoned mine sites, we have the problem of what are we going to do as a walkaway solution, and there really has been very few of those, if any. Next question, please.
Can I, if I can, just for a second, comment on the same issues. Tailings, it's an issue of integrity of the dam, and I don't think it's reasonable. I think we have to be cautious when we say designing for infinite time. So that's a real issue. I think design aspirations might go there, but practicality is not necessarily there. So for tailings, saturation by water is a very good solution. If you can maintain that for a long time, that's great. In Canada, there have been some examples around the world of subaqueous disposal in natural freshwater systems and in marine systems. And you know, that's pretty offensive to a lot of people, because you say you're going to dump those tailings in that beautiful lake, and you have to understand that reaction. But if you want to think into the long term, that is probably the most stable setting, because it's a natural basin, and you don't have to worry about dams and whatnot. So that's one option, and you know, you can argue about the pros and cons and so on, but the tailings have to remain saturated. If you can't do that, if you have dam failures, then you've got a problem, a big problem. As far as waste rock goes, you're dead on. It's a water management issue, because you can cover them, you can add carbonate, you can do all sorts of mitigating measures. You're never going to stop that bleed of if there's oxidation, if they're exposed subaerially and the water table is low, then you're going to get some leachate that is, you know, for these types of materials, likely going to be acid generating and metal containing. So you've got to maintain some sort of facility to look after that water. It's water management. And in Canada, we get closures on mine sites, and we call it perpetual treatment. And as Kirk says, it's line treatment plants, and companies commit to perpetual treatment. And you know, what does that really mean? Time will tell. Right.
Okay, we're running out of time, so we'll just take two more questions. Please keep them focused.
Okay, Phil North, Environmental Protection Agency. And I'm wondering if you could touch a little more or discuss a little more on the mine workings themselves, the pit, or if it were perhaps an underground mine, and the implications of the data for there. You've touched on it a little bit, but it would be interesting to hear what the longer term implications are.
Okay, I guess I can't really say too much about the longer term implications until we've kind of gone through the process of scaling up from our laboratory test work to the kinds of scenarios that we are talking about in the field. In terms of a pit wall, for instance, we would need to know exactly what the composition of the pit wall is, and that sort of information would be available once the mine plan's finalised, because they'll have a model of, you know, where the pit volume actually resides, where it's located, and there'll be some way of mapping, if you like, the composition of the pit wall surface. And basically what we would do then is have a look at what proportion of the pit wall surface was sulfide bearing, and again there are engineering options here to perhaps manipulate the final pit volume so that you minimize the amount of exposed sulfide mineralogy. So again, there are questions there that you know, feed into the mine planning evolution. But anyway, having determined the proportion of the wall rock that's sulfide bearing, we then need to find some way of applying a rate of oxidation of that wall rock versus the rate at which rain, for instance, is rinsing that pit wall surface. And that's going to give you some degree of quantification of a source term, we might call it, so a contaminant source term that's represented by that pit wall, and that needs to be put into the context of an overall kind of site water balance, like what volume of contaminated water does that runoff actually represent, and when you mix that in with all the other water sources at the site, you know, how important does that particular contaminant source become compared to other potential contaminant sources? And these are all questions that would be addressed as we kind of go forward with the water quality predictions.
I wonder, are there analogous situations? The Berkeley pit in Montana is the famous, you know, acid pit, and are there other examples where there's maybe they could be drawn as parallels?
There are bound to be some examples, perhaps in some of the Canadian porphyry examples that Steve has reviewed as part of the review. I'm afraid I'm not totally familiar with the detail of those sites and whether there were pit lakes or not, and whether those pit lakes were acidic. It's all going to be a matter of the quantity of acid that's being generated on the pit walls versus the amount of dilution of that acid by other water sources. So it'll all come back to the water balance, if you like, for the particular site in question. And for this, you know, for a conceptual pit at Pebble, I don't really know what that water balance is, and therefore what the relative importances of the different sources of contaminants would be.
Thank you.
Yep. Do we have one more question?
Thank you. Philip Applecock Sr. from the Michigan River. On the waste trucks, when after they're in mines that are already in operation, the contaminants and acid is there, and you guys take them up and you guys put them in a pile, and you guys be able to drain them out and take the acid out, and in the reclamation, how many years you got to be able to use that rock to be able to put it in a reclaimed area that is not contaminant when you reclaim it and replant that area to as is. And the water in the mine that are already built, you got to be able to run that. After you take the gravel, you got to run it through and be able to put it in a system and be able to put some material in there to separate the gold from the precious minerals from the material, and you use some chemicals, and then you got acid. Then you create another acid waste tailing is gravel. And the other question is on the water. You got it's contaminant water, and in order for you to be able to filter that water within a climate as Alaska, you got to be able to build something to be able to filter that water out. So when it comes out in the end, it got to be contaminant free. And I think that's the fear that, and you got to be able to at least one more thing is you guys say that lining lasts for many years, but you guys got to be able to see that if a big enormous gigantic mine it's going to be built here, and you're looking at gravel waste that's going to be billions of tons, and you got water. You got to be able to put them someplace. How long will that lining last? And you're talking about a critical area. Thank you.
Claire?
I think the question was focused on, I guess, how confident we were that either the solid waste streams, the different kinds of solid wastes on the one hand, or contaminated waters on the other hand, how confident we were that those kinds of materials could be managed in the long term in such a way that the wider environment was protected. Is that fair? Is that what the...
We're dealing with water that's cold, and in Alaska, the winter months are not 6 months long. Now they're eight months long, and in the 30s and 40s they were 9 months long. Climate changed it down to 8 months long. They're not 6 months long. And on the water tailings, you got to be able to, let that water go to a system before then it'll be able to come out, contaminant free, and you could be able to at least put it back, and there'll be no contaminants in that lake, or will there still be contaminants as in the gravel tailings?
I think ultimately where you're going is what should be the performance criteria that the project can be judged on in terms of the local water quality, and I get those performance criteria. I believe have still to be agreed, decided upon. I can't comment on them myself. It's kind of outside of my area. The type of work that we've presented here was really, I guess, basic geochemical characterization work that's to be used to help understand long-term behaviours. But in terms of putting closure strategies into place and identifying the performance criteria that those strategies must meet, that's a process that I believe has yet to take place, but perhaps somebody from the Pebble project can say something on that topic. Or maybe not. It's kind of outside the scope, I think, of this particular discussion. Certainly it's not something I personally can talk to. Oh, we've got...
Yeah, well, I mean, I think Philip is concerned about a whole range of different issues, all of which you've talked about here, and all of which I think, we're going to have to address as we develop the mine plan. Water treatment is pretty sophisticated these days. So, testing to find out what we actually have to deal with, which is part of the work that's been done here, is essential to our understanding how we have to design the water treatment plant. The state has very high requirements for what we can put back into the environment, and we will have to meet those. And at least at this point, we're going to have to meet them long term. And how we fund that is an issue that will be developed during permitting. In terms of how things like waste pellets are going to operate over the long term, I think that's part of why we're doing some of this work. But those are issues, and what you do with some of that in the long run, whether you process it at the end, whether you put it back in the pit, all those issues are still things that need to be considered. But in the end, we have to design something that we believe does not allow things like acid and excessive minerals to get back into the ecosystem. That's the challenge. And I know some people think we're delaying producing a mine plan for all sorts of nefarious reasons, but this is a very complicated project, as we've seen, and so we're taking our time to try to get those answers right.
Thanks, John. Now we've reached almost the end of the first panel review on geology and geochemical characterization.